Hello friends, so today we will learn how Mohr Circle is used in rock deformation. So the role of Mohr Circle in rock deformation. Today topic is Mohr Circle in rock deformation. Mohr Circle in rock deformation. So today we will learn Mohr Circle in details. So before going to Mohr Circle, we will study rock deformation. So what is rock deformation? Rock deformation. Deformation of a rock means any changes of rock in terms of shape or size due to apply of external stress. Then we call that rock a deformed rock. Changes in rock. Changes in its original form. Changes in its original form due to external external stress or force. Okay. So these changes may be due to size. So the changes may be on its size or shape. Any changes found in the rock from its original shape, we will call it as a rock deformed rock. Okay. So in deformation, we'll study in rock deformation. We'll study three terms. Dynamics, kinetics, kinematics. So in these three terms, dynamic, kinetics and kinematics, these three terms are used in rock deformation. So the rock deformation will be understood by using these three terms. Okay. So dynamics. So let's understand how these three terms are correlated in deformation. So this is a person called, his name is Ravan. This is Kaliyug Ravan. He is very upset. Why? Because Ram punched him. This Kaliyug Ravan was punched by Ram. So when Ram punched Ravan, it got a scar on its face. So that's why he is very upset. Okay. Now we will see these three terms: dynamic, kinetics, and kinematics in this cartoon. So dynamic is what? The force it is applied on Ravan's face is the dynamic. We'll study about the force or stress. Okay. The study of stress at which Ravan was punched is your dynamics. And the speed at which Ram punched is called the kinetics. And the scar it got on his face is called the kinematics. Okay. So now the force at which Ravan was punched is called the dynamic. The study of the stress or the force is the dynamic, and the motion and the speed at which the punch was moving is the kinetics. Study of the motion is your kinetics, and the scar it got on his face is the study of the strain, that is called strain. The scar is called the strain, and the or the study of the effect of the stress is strain. So dynamic at which the he paused, or so dynamic is the study of the stress, and kinetic is the study of motion, and the kinematic is the study of the effect of stress, that is strain. Okay, so under dynamic we will study stress, study of the stress at which the rock deform is called the dynamics, and the motion at which the rock and the force was applied, the motion at which the force was applied is called the kinetics, study of motion, and the effect of stress due to the applied force is called the study of kinematic, or the effect is known as strain. Effect of stress is strain. So these three terms will cover the rock deformation. Okay, so under dynamics we'll study fracture, fault, joints. So these are the terms we'll study under the dynamic of rock deformation. In kinematics of rock deformation we will study shear zone, mylonites, foliation, lineation. So these are the term we will study under the kinematics of rock deformation. Okay. In dynamics we will study about the stress, or that is the brittle deformation. So these are the product of brittle deformation, fracture, fault, joints. And under kinematic we will study about the ductile deformation, where we will study shear zone, mylonites, foliation, lineation. But under kinetics we will study about the motion of plates. So motion of plates means we will study about the tectonics. The motion of plates will be covered under the tectonic section. Okay. So first we will study the stress. In geology, we study stress but not the force. Why? Because in geology we will study about the rocks, the deformation of rocks. So any kind of stress or force is applied on the rock. So since rocks are not freely hanging or freely movable, they are attached to the base of the earth surface. So whenever we apply a force, or whenever a force is applied on rock, there is also another equal opposite stress is applied from the other direction. Equal same amount of force is applied from the opposite direction. That's why we call it stress. Suppose this is a rock body, and this rock body is attached to the earth surface. So whenever we apply a force vertical, force on the rock surface, the same amount of force is applied from the bottom also, from opposite direction. So that's why we call it stress instead of telling it force, we call it stress. Stress is applied from opposite direction on from both sides. Okay, and since this force is applied on surface also, so we call it as a stress. So stress is what? Stress is force for area. Okay, so therefore we always use the stress in, we do not use the term force, we use always stress. Stress is applied on the rock body. Okay, now the maximum stress we applied from vertical is, we call it as sigma 1, and there is also another less amount of stress is acted perpendicular to the sigma 1, we call it as sigma 2, which is minimum. Okay, you must have experienced when you try to, suppose you want to cut a wooden rock. Okay, long wooden rock, you want to cut it. So what you do is you try to hammer it on vertically. Okay, simultaneously, and that vertical apply of force or stress is your sigma 1. But simultaneously you also put your leg on the rock so that the wood will not slip away. Okay, so that force we applied, which is minimum force, we do not apply the maximum force, we just to for the support we use another force on it from lateral side, so that the rock will be stable and it can be break smoothly. So that force we applied laterally by putting our leg is your sigma 2. So therefore sigma 1 and sigma 2 are perpendicular. To give this rock body a stable position, these two forces applied perpendicular to each other. Okay, one is the maximum, which is called a sigma 1, and the minimum one we call it as sigma 2, and these two are perpendicular. Okay, so we understood sigma 1 and sigma 2 are applied in this rock body. Okay, now the rock will fail at certain angle. Suppose this is a failure plane or fault plane, fail at some certain angle theta. Okay, now the rock fails. The rock fails not because of the sigma 1 and sigma 2. There is two other stresses which are played the important role to break the rock. Okay, suppose these two stress we call them normal stress sigma n, normal stress, another one is shear stress. Okay, normal stress means perpendicular stress acting on the fault plane, and another is the shear stress, which is parallel to the fault plane. Now let's feel the normal stress and shear stress. Okay, suppose I am pushing this my palm with the finger. Okay, and perpendicularly I'm pushing it perpendicular, so I feel my hand will feel the maximum stress because I am applying force perpendicularly. Okay, when it was perpendicular, you are just experiencing only the normal stress. Okay, normal stress. But when you tilted a little bit, make an angle, then you feel that you are both having the normal force as well as a slipping force. Okay, so this these two forces, normal forces and slipping forces or sliding force, is acted on the rock body on the failure surface. So the normal force is acting perpendicular to the failure plane sigma n, and the shear force which is parallel to the surface plane called as shear. So these two stress, normal stress and shear stress, helps to break the rock. Okay. So whenever you apply sigma 1 and sigma 2 on the rock, on this rock, you will feel these two stress. One is normal stress and another one is shear stress, which is parallel to the fault plane. This combination of these two forces will help to break the rock at angle theta. So whenever you change the theta, suppose you change the theta another angle. Similarly, the normal stress also changes and the shear stress also changes. So for different angle of the fault plane, or so you will experience different amount of normal stress and different amount of shear stress for different angle of the fault plane. Okay. So different fault orientation of fault plane, you will experience different combination of different normal stress and shear stress. So whenever we try to fail a rock, so there the failure of the rock depends upon the these two stress, normal stress and shear stress. So the combination of these two stress actually helps to fail the rock body. Okay. So the importance here is the normal stress and shear stress. So we will calculate normal stress and shear stress for a particular theta. So suppose this is our rock body, rectangular rock body. A, B, C, and D. We apply sigma 1 maximum stress from this direction and minimum stress from this direction, sigma 2. Then the rock fails along the SC plane, making a theta angle with the AB. Okay. Since we know that the normal stress and shear stress both are the function of theta, sigma 1 and sigma 2. So the normal stress and shear stress both depends upon this theta, sigma 1, sigma 2. So we calculate the sigma n by taking this sigma 1, sigma 2 and theta. Okay. We will calculate these two stresses by using this theta, sigma 1 and sigma 2. Okay. Since sigma 1 is acting perpendicular to the AB surface, so we can say that sigma 1 equal to f of AB upon area of AB. Sigma 1 equal to f of AB upon area of AB. Sigma 1 stress equal to force per unit area. So the force applied on this surface, AB surface, is f of AB and the area is A of AB. Okay. Then the force on AB is sigma 1 into A of AB. Similarly, the force sigma 2 is acting on this BC surface is f of BC and the area is A of BC. Similarly, f of BC will be sigma 2 into A of BC, area of BC. Now the force, that is f of AB on the SC plane, when it acts on the inclined plane, it will resolve into these two components, normal component and shear component. Okay. Similarly, this force f of BC on this inclined plane, theta plane, that will also resolve into this normal stress and shear stress. Now this is theta and the angle between this will be theta. Okay, so this is perpendicular to the AC plane, so this is theta, means this is 90 minus theta, and these two are 90 degrees, so if this is 90 minus theta, then this will be theta. So this is our theta. Okay, and this will be 90 minus theta, and this will be over theta. Okay, so this is f of BC. Now we will calculate total normal force on AC, not stress, total normal force on AC. So total normal force on AC plane. So what will be that? The normal component by f of AB and plus the normal component by f of BC. Okay, so total normal force on this AC plane will be how much normal force by f of AB and how much normal force by f of BC. So normal force by f of AB plus normal force by f of BC. For this vector f of AB, this f of AB, this vector can be resolved into two components, this perpendicular component and this shear component. This normal component f of AB can be resolved by into f of AB normal component, f of AB shear component. Similarly, f of BC, this component can be resolved into a normal component and shear component. Then f of BC normal component, f of BC shear component. We only required how much normal components are acting on this AC. So normal forces by f of AB plus normal component by f of BC. Okay. So now what is the normal component for f of AB? F of AB cos theta. Okay. Since this is theta, this component will be f of AB cos theta. So this will be f of AB cos theta. And for this is 90 minus theta. So f of BC cos 90 minus theta for this plus f of BC cos 90 minus theta. This is for a BC normal component, or we can write cos of 90 minus theta is sin theta, right? We can write sin theta. Okay, now we can replace this f of AB by this and f of BC by this. What is this? Is sigma 1 into a area of AB and cos theta plus sigma 2 area of BC sin theta. Okay. Now consider the triangle A B C triangle. Okay. Now consider the A B C triangle. A B C triangle. This is the triangle. Okay. Now cos theta is how much? Cos theta is B by S. B is this AB by AC. AB by AC. Then AB equal to AC into cos theta, right? This AB is length. We can replace it area of AB. We can replace all term into area. Okay. area of AC into cos theta. Similarly, sin theta will be how much? Sin theta is equal to BC P by H, BC by AC, BC by AC, or BC equal to AC sin theta. Okay, convert it into area. Area of BC equal to area of AC into sin theta. Okay, now replace this term, area of AB, by this term. Okay, by this term. Similarly, area of BC will replace this term, area of BC, by this term. Now how much? Sigma 1 into area of AB. Instead of writing area of AB, you can write area of AC into cos theta, and this cos theta is also already there, cos theta, plus sigma 2, area of BC is here, area of AC into sin theta, and the sin theta is already there, sin theta. Now is how much? So this is sigma 1 area of AC cos square theta plus sigma 2 area of AC sin square theta, right? So what we are doing, we are calculating the total normal force on AC plane. We are calculating total normal force on AC plane. This is your AC plane, this is your normal stress, and this is your shear stress. Then normal force, since sigma n is a stress, so that will be your perpendicular, since this is a perpendicular stress, so this will be perpendicular force upon area. Area is area of AC, no? Area of AC. Similarly, for shear stress, we can write stress equal to parallel force, all shear force upon area SC. So now forget this term, we'll focus on this term. So sigma n, so total normal force is how much? Sigma n into area of SC. Okay. Now total normal force, we will replace this total normal force by sigma n and into area of SC. So we can write here sigma n into area of SC instead of this total normal force on SC is this much. Now see, in this equation, ASC, area of AC is common. Okay. Now got this area of AC, and how much? Normal stress equal to sigma 1 cos square theta plus sigma 2 sin square theta. We got this term, right? Okay. Now write it. Sigma n equal to sigma 1 cos square theta plus sigma 2 sin square theta. Okay. Now we'll replace this sin form to cos form. Okay. In trigonometry formula, we know this, that sin square theta equal to, in trigonometry you know that sin square theta equal to 1 minus cos square theta, or this term will be sigma 2 minus sigma 2 cos square theta. Now taking cos square theta common, sigma 1 and sigma 2 cos square theta plus sigma 2. I can write this. Okay. Now in trigonometry, there is another formula, cos 2 theta formula. Cos 2 theta equal to 2 cos square theta minus 1. Then cos square theta is equal to 1 plus cos 2 theta by 2. Now replace this sigma 1 minus sigma 2. Okay. 1 plus cos 2 theta by 2 plus sigma 2, or you can use 2, and this will be your, now what we can write is sigma 1 minus sigma 2, 1 plus cos 2 theta plus 2 sigma 2 whole open 2. Now simplify this. This is this and this is this. And then sigma 1 minus sigma 2 this, and then sigma 1 minus sigma 2 brackets cos 2 theta plus 2 sigma 2 by 2, and then this will be 2 sigma. So we can write sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta. Can we write this? So here 2 theta, 2 sigma 2, 1 is cancelled, so sigma 1 minus plus sigma 2 divided by 2, separate, we separate this 2, so this will be, so this is the normal stress. So this is your normal stress, and the formula is normal stress. So this is your formula of the normal stress. So sigma 1 plus sigma 2 upon 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta. Okay. So this is for sigma n, normal stress. We calculated formula for normal stress. Now we'll calculate formula for shear stress. Okay. Shear stress. Similarly, we will calculate shear force on AC plane. So total shear force on AC plane. Total shear force, not stress, okay, on AC plane. This is how much total shear force on AC plane. Okay. In this F of AB acting, and on this direction F of BC. Okay. So this F of AB can be resolved into a normal stress and a shear stress. Okay. And this is shear theta. Similarly, the F of BC can be resolved into a normal stress and a shear stress. This angle is theta. Okay. So the total shear stress, or sorry, so the total shear, so the total shear force on AC is this one plus this one. shear force by F of AB and shear force by F of BC. So we write shear force by F of AB plus shear force by F of BC. Okay, but here the important thing is this sign. Okay, so this shear force is acting like this, and here the shear force is acting like this. These are two different kind of shear forces. In geology, let's draw it again. This is one kind, and this is another type. Okay, since this indicates a dextral shear. Why dextral? Because when you stand on the fault plane and looking towards the fault, the arrow which is coming towards you is the will accordingly name it. Okay, if it is coming towards you, then that is towards your right side, then that is dexter. In this case, if you stand here and look towards the fault plane, then you will see that the arrow is coming towards you is the left side. So this is left sense of shear, or we called it as sinistral shear. Okay, in this case, suppose you stand here. Wherever you stand, you look forward towards the fault plane, then the arrow which is coming towards you, remember, the arrow which is coming towards you, accordingly you will name this. In this case, this arrow is coming, the right side arrow is coming towards you, so this is right sense of shear or dextral sense of shear. Similarly, if you stand here, the left side arrow is coming towards you. If you stand here also and looking towards the fault, then the left side arrow also coming towards you. So that is left sense of shear or sinistral sense of shear. In geology, for dextral we'll take it as positive, and for sinistral we'll take it as negative sign. Okay, that is the sign convention. Okay, so in this case we take positive because this is a dextral sense of shear, but in this case we will take negative. Why? Because this is sinistral sense of shear. For shear force for F of FB, this one will take positive, and shear force for F of BC, this one, this is sinistral, will take negative. So instead of taking positive here, we'll take negative sign. Okay, so this is the convention in geology. So now so the shear force for F of FB is F of FB F of BC. Okay, this angle is theta, this angle is theta. Okay, now the shear force for F of FB is this one, so we'll consider this one. So this is your, since this is theta, so we will take this one. This is F of FB cos theta, this is F of FB sin theta. F of FB sin theta minus shear force by F of BC will be, this F of BC will result into 2 normal stress and shear stress. So this one is for f of bc. Since this is theta, this will be f of bc cos theta. F of bc cos theta. Okay. The always attached one will be your cos theta and the other one will be your sin theta. Okay. So now we'll replace this term f of ab by this f of ab, this one. Okay, sigma 1 ab cos theta. Similarly, we'll replace this f of bc by this sigma 2 ab cos theta. Now replacing this one is sigma 1 area ab and sin theta is there, minus f of bc sigma 2 into area of bc into cos theta. Okay. Now we are calculating shear force on AC, total shear force on AC. So total shear force on AC, this is AC plane. Okay. This is a normal stress, and this is your shear stress. Okay. Now total shear stress on AC will be total shear force. Okay. Now since here this is a stress condition, stress, so force per unit area, stress is force per unit area. So force is total parallel force or shear force on AC plane divided by area or area of AC, or total parallel or shear force on AC plane equal to shear stress into AC. So here we can write total shear force on AC, we can write this one. So here we can write this one, shear stress area of AC. Okay. Now we'll replace this term, this area of ABC term. Okay. How? Now taking this ABC triangle. Okay. Taking this ABC triangle, ABC triangle. This is theta. The cos theta. Okay. Cos theta equal to cos theta B by H AP by AC, or AP equal to AC cos theta. This is line. We can take area on both sides. Instead of line, we can take area. Similarly, sin theta equal to BC by AC, BC by AC, or BC equal to AC sin theta. Instead of line, we can take area of both. Okay. Now we will replace this term by this, and this area of BC by this term. Okay. Now see what happened. Okay. So the sigma 1, instead of area, you can write this area of AC. Okay. This one, area of AC equal to, so sigma 1 area of AC cos theta. Sorry, the sin theta is there. Sin theta minus sigma 2 area of AP equal to AC, area of AC sin theta, and this cos theta is already there, cos theta. Since area of AC is common in all cases, so we can cancel this. Now shear stress is sin theta, and sin theta cos theta is common, so we can take sin theta and sin cos theta common, cos theta. Okay. In trigonometry, we know that sin 2 theta equal to 2 sin theta into cos theta, right? In trigonometry, we know that Sin 2 theta equal to 2 sin theta into cos theta. We can replace this sin theta into cos theta by this. So now how much sigma 1 and sigma 2 by 2 sin 2 theta. So this is your shear stress. Now this is, now you got the formula for the shear stress. Okay, so this is your formula for the shear stress. So from this we have calculated this normal stress and the shear stress. Okay, now the formula for normal stress we found is, normal stress is, remember, sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta. Okay, cos 2 theta. And shear stress is sigma 1 minus sigma 2 by 2 sin 2 theta. So these are the formula we have derived from this this rectangular object, where sigma 1 and sigma 2 perpendicular and taking theta. So sigma, normal stress and shear stress, stress and shear stress both have the function of sigma 1 maximum stress, sigma 2 minimum stress, and theta, breaking angle theta. Okay, so the whole lengthy process we have used for this calculation of normal stress and shear stress. Okay, now we'll see how Mohr help us, Christian Otto Mohr, how he help us to find out this normal stress and shear stress very quickly from his graph. Okay, he has a graph. He has taken normal stress on x-axis, shear stress on y-axis. From this graph, very easily we can calculate normal stress and shear stress. We do not need to write all the lengthy process for this calculation. Okay, we'll see it later.